Thank you. Howdy, folks, and thank you for joining. Thank you, Professor Romiński, for a warm welcome. This presentation, Python for Machine Learning, will be an introduction to Python for machine learning, but also to some of the tools that will be used in other sessions led by other speakers as well. So I hope you will find it helpful and that it will aid you to make the most out of this school. As this is the first session that even precedes the introduction to machine learning, we will be mostly focusing on what and how to use to achieve certain results, rather than dive deep into the math behind it. In this session, I'm making an assumption that you have at least a very basic understanding what Python is and that you have used it at least once. But nevertheless, I will try to cover some of the basic principles of Python programming language as well. I will not cover all of them in this session as it's far too short to allow for it, but instead I've handpicked some of the topics that I think are particularly useful when applying Python to machine learning oriented tasks. Also, as actually this is the middle of the night here, it's 3 a.m. If at any point you think that I'm diverging from the topic or I'm silent for an extended period of time, please let me know in chat. The chat should buzz, and I will come back to the world of alive. So as you may have noticed on the previous slide, and as Professor Romiński introduced me, I'm Maciej Szankin. I'm a Pole living and working in the United States. It's a Pole with a capital P, so that's more like it. I'm a deep learning software engineer working for Intel in San Diego, California. My work focuses on deep learning for computer vision, and more recently, I've been involved with NLP a little bit more, and also related optimizations for a CPU and more resource-constrained devices using different hardware accelerators. So before we even begin talking about programming and machine learning, sorry to stop, but answering one of the questions, all presentations will be uploaded to Google Drive. All the videos will be available on our website, and all the materials should be available on the Google Drive later. So right now I haven't shared my presentation yet, but I will get to this point, and I will share it later, so everyone can follow at their own pace after this presentation. So yes, all the materials should be available later. Where was I? Let's start with what is needed to get the most out of this and the following sessions. First of all, just as Professor Romiński mentioned, if you haven't yet created an account on our Slack, please do, as all organizational stuff will be announced there in the channel. And also, it's a great way for all of us to communicate and stay in touch. You can post the questions and answers at the time outside of the sessions. And also, as this presentation is related to machine learning, and if you have any questions to me or questions related to the topic that someone else can answer, please post them there. Right now, obviously, you can post them in Zoom, but if it's after the session, please feel free to post them there in Slack. All other sessions also have Slack channel set up. So if you ever feel lost which channel to use on Slack and how to get to the speaker, please go on to our schedule, which is available on our website, 2020 dl-lab.eu. And if you go to the virtual summer school tab, you will see the schedule. And for your convenience, we've grouped the sessions together according to their field or topics. So for instance, my presentation is kind of in the machine learning field. So all related questions, or if you want to get in touch with me, you can do it on the machine learning, the hashtag ML channel, and the same for the next presentation done by Professor Romiński, which will also be in the machine learning field. So if you have any questions to Professor, just go to this channel and will be there for you. So next thing is getting the environment set up. There are a few things for you to consider. One, you can obviously use your own machine and install all packages there. Or two, you can use one of the remote services that we'll go through briefly. So the first option, running locally. For this, you will need a Python interpreter installed in your system, which I hope everyone has already installed. If you are a Linux or Mac user, there is a high chance that you already have it installed. For Windows, as far as I'm aware, you have to download the installer and do it yourself. But in any of these cases, please don't stop here, as usually the default installations are not the best for you. They are the best for generic or a common case, but you're not a common case, right? So there's this thing called Anaconda. You might have also heard it during being referred to as just Conda. What Anaconda is, it's basically a Python distribution. So if think like Anaconda is Ubuntu and Python is Linux. It's a relation just like this. It's really great as it does solve a lot of issues with which you may encounter, especially in the data science field and setting up your working environment. The main selling point is that it not only allows for managing Python packages, but also additional libraries and drivers. So you no longer have to go to the hardware manufacturer's website, download the drivers or a library, go through installation process manually, only to discover that the Python package you want to use requires older driver version. I've been there so many times, and I did break a lot of systems while resolving dependency hell. So discovering Anaconda for me felt like a breeze after a firestorm. When you use Anaconda, as it's a beefier management tool for Python, but it still keeps all the tools that you would expect to be available from Python. So you still have access to Python tool that everyone know and love. It's called the pip, which stands for pip installs packages. And actually, I just recently discovered what pip really stands for. So far, I've always thought that it's package installer for Python, but apparently I was wrong for many years. So another great thing about Anaconda is that it's great bang for the buck. Not only because it's free, but also because many of the existing Python libraries have been rebuilt for Conda, and so they will outperform pip installations. When you install using pip, you get a Python package that matches your CPU architecture and the operating system that you use, but that will be about it. And with CPU, there's far more to consider than simply 32 or 64-bit architecture. Packages available through Conda have been built against additional libraries and with extra flags, thanks to which you are not getting a generic package that runs on 99% of the machines on the internet, but rather a package that targets a group of machines similar to the one that you are using. It's like having a package built from source, but without having to meet all the dependencies manually and going through the very iterative process of discovering which build configuration works the best for you. If you have Intel CPUs, most of the packages like NumPy, TensorFlow, PyTorch, installed through Conda will include this kind of optimizations thanks to the Intel's MKL, the math kernel library. And so it's a great way to boost your system's performance without additional step being needed. Anaconda will install most of this stuff for you. And also, if you want to have the latest and greatest improvements available through Conda, you can go and look for Intel distribution for Python. It's an environment built around Anaconda. It has a more targeted package channel than the Conda's main channel. So if you want the latest and greatest improvements for all the libraries that you run, you can try this channel out. But from what I have seen, most of those improvements either will make its way into the Conda's main channel. So if you wait long enough, you should be enjoying them as well while being on the main channel of the updates in Conda. Someone draw a line on the screen. Okay. now that you all should have Python installed, either from your system or Conda, functionality-wise, it doesn't matter really for this presentation. You will be able to follow using either of these. To follow this presentation and the following ones, you can either just write a script in your favorite editor and run it in command line, or if you prefer, you can use Jupyter Notebooks. If you've never heard of Jupyter Notebook, basically what it is, it's a browser-based environment which allows for executing Python scripts, but not only, it also supports some other languages. While remembering that state of each of the snippets, the Jupyter Notebook will remember the state of each of the snippets. So you don't have to run them again, at least not within the same session. If you restart the session of the Jupyter Notebook, all the information will be gone and we'll have to rerun some of the cells, but we'll go through it soon. So the Jupyter Notebooks are one of the most popular tools in data science, and they allow for expressiveness in your code. As you can very easily mix scripts with documentation written in Markdown, and you can even plot charts in between the cells. You can get Jupyter Notebook installed by running either of these commands that you can see on screen. For the functionality-wise, it doesn't really matter, but just as I said, if you install most of the packages through Conda, they will come with built-in optimizations and overall should perform better than the ones installed from pip. So in the next slides, we'll go through different ways of running notebooks, and then we'll talk about them a bit more into detail. And answering one of the questions, is Anaconda necessary to be installed prior to use Jupyter? No, it really doesn't. You have to have Anaconda installed in order to use the Conda command. But if you just have Python, virtualenv, or the pure Python, you can just follow these and other presentations using pip and virtualenv. Either way, with virtualenv or Conda, you have a better management of the environment, so you don't mess up your system in the global settings. So this is something to consider, but you can just use virtual environments. There's also another question: what is the purpose of using Miniconda? Anaconda is this Python distribution system. It has two versions. The first one is the main one called Anaconda or Conda, and the other one is Miniconda. Both of them will allow you to do the same thing on your system. They will both come with the same management system. So Miniconda compared to Anaconda is more like a stripped down version of Anaconda. So it doesn't come with all the default packages, but you can still get them installed using standard installation command utilities. So it's more like a more lightweight thing to use. Okay. So if you're using local installation, you just have to run Jupyter Notebook command in the directory which you think is worthy of being your workspace directory. And basically that's it. If you go to the directory, type the Jupyter Notebook in your command line, hit enter. It will take a few seconds, and after a moment, a new browser tab should open. And if this is your choice, just hang in there. We'll get back to the notebook in a moment, and we'll go briefly through how to actually use it and what's the functionality that it gives it. But for now, yeah, you don't really have to install anything locally if you don't want to. You can use one of these remote services, which allows for hosting and running your code on someone else's computer, either in cloud, in case of Google Colab, or on our server deployed in the university in Gdańsk, which we just call ML or ML server. So the first of the remote ways is to use Google Colab. So the Google Colab is available at this website. So if you go to the colab.research.google.com, let me go there very quickly. Have it. It will give you a short welcome screen from there. If you have used it, it will give you a list of notebooks that you've already used in the past. And if you haven't, you can just go ahead and create a new notebook. And the experience that you will get in the Google Colab will be very similar to the one that you will get on your local Jupyter notebooks. The Google Colab is basically a Jupyter notebook on steroids. It has a little, some of the things are a little bit different, but only a little bit. Most of them, they share both Colab and Jupyter notebooks. They share a lot of common things, so you shouldn't feel too lost. And great thing about Google Colab is that obviously it's free, so you can use it wherever you are in the world. So that's great. It offers different environments. You can base your environment on a CPU, GPU, or even the TPU, which is the tensor processing unit. And if you want to change the backend, hardware backend for your notebooks, you can go to the runtime and change runtime type. And then the window will pop up and you can select the hardware accelerator that you want to use. If you select none, you'll be running on the CPU, but you can also select the GPU and the TPU if you want to. So the thing to remember about Google Colab though is that the resources are not guaranteed. So it's more like a first come, first serve basis. Although Google has a lot of resources, so I really haven't seen a situation in which there was none to use. But still, you should avoid hogging resources because other than first come, first serve, there's a little bit of scheduling going on. And actually, you can get a lower priority in the future if the amount of requested resources that you got, if they are not actively used, then you can get a low priority on the list. And also for improving experience, you can use Colab Pro. It's a paid service. I don't remember, but I think it costs like $10 a month, and it will give you access to better hardware and a higher priority on the resource waiting list. So this is something to consider if you are into using Google Colab. When using Google Colab, you can execute bash commands in a cell. If there is anything missing, you can even use it to install new packages. You just have to prepend your command with exclamation mark, and this command will be running in a shell. So if you want to install a certain Python package, let's say wget, you just have to type in exclamation mark pip install wget in the cell, run the cell, and you will get wget Python package installed. And also another thing that's it's worth mentioning that if you quit your browser or tap with the Google Colab, the environment will be cleaned upon exiting. So if you have a lot of dependencies that you want to install and then use, then you can make your life a little bit easier. And the first cell can be your cell where you list all the dependencies that you want to install and have all the commands there. So when you come again to this notebook, you can have them reinstalled in no time. The ML server, there have been some questions in the chat about the ML server, so I hope that I will answer them briefly on these slides. So the ML server is a very similar concept to the Google Colab. There is this thing called Jupyter Hub, which basically is a clusterized version of the Jupyter Notebook. It allows to run multiple notebooks for multiple users at the same time. So this is the kind of setup we use for the school. The server is located in Gdańsk, so if you're somewhere else in the world than Poland, you can still use it, but depending on the distance, your experience may vary due to the latencies and networking issues that might occur. So I would advise it to use it if you really can't use Google Colab. You can use either of them to follow any of the lectures in the school, so you should be fine with either of these choices. And to actually get access to the ML server, you need a user account. So if for any reason you want to use this ML server, don't be shy. You can reach out to me, and I will gladly assist you with creating a new account. And You can PM me on Slack. Once again, my name is Maciej Szankin, and if it's hard for you to remember, you can go to the general channel on Slack, and you will find me as I've been posting announcements there before. So just click on me and send me a message. So on the mail server, you can still execute bash commands in a cell, just as in Google Colab, but actually you can't install new packages. We just don't have the scale to give such wide permissions, so we try to go ahead and pre-install all the required packages ahead of time for all the users. But if you want to experiment and install something new, unfortunately, it's impossible on our server. So when using the Jupyter Notebook, it's nice to familiarize yourself a little bit with the environment, as it's a little bit different than using Python in a command line. So for instance, yeah, okay, so we have started. So either if you are using Google Colab or if you're using your local Jupyter, you can create a new notebook. You can follow this presentation using a clean notebook. I will share all the codes later today, but I thought that it would be better if I do not share all the codes too early, as this will keep you maybe more engaged in all of the sessions. So if you want to follow, you can just create an empty new Jupyter notebook, either in your local installation, or you can go to Google Colab and create a new one. It doesn't really matter. So here you can see that we have a cell. So within each cell, you can write different Python expressions. You can run the cells with either hitting run button here, or there's a keyboard shortcut. Can you please zoom out the screen? I will try. Yep. Yeah, okay. So when you write the code in a cell, you can either hit run in the UI to execute the code in this particular cell, and only in this cell. It will not run the whole notebook. Or you can use the Shift-Enter shortcut, and you can run it without having to use your mouse to click at anything. There are all kinds of commands that you can access with commands Shift-P or Control-Shift-P, depending on the system that you use. And here you'll find all the useful shortcuts to operate within the Jupyter Notebook. I've also listed some of them on the slide, so you can use it as a, about that. Yeah, I'll have to jump in and out of the Zoom. You can use all those commands to make your experience with Jupyter Notebook a little bit easier. So just as I said, within the notebook, it can use the bash commands in a cell. You just have to prevent them with an exclamation mark, and you can basically run all the bash commands that you want. You can list the current directory, you can install packages and stuff like this. If you don't want to use, if in general your notebook uses Python, but you want to use some different language backend in a particular cell, and this language is different than Bash, you can use 2% marks and then one of the options available here, and this will make this particular cell run using a different language. You can also write LaTeX formulas in your notebook. So if you want to have a little bit of more mathematical documentation, you can use it as well. So let's go here. So there are actually also worth mentioning, there are two different types of cells. By default, any cell that you create and run, it's a Python type of cell, but you can switch the type of the cell to also a Markdown and to others that are not relevant right now. But Markdown basically is a nice way to document your code. So if you have any description, you can, to your function, you can just insert it there, and it will make your code more expressive and readable. You can also use a keyboard shortcut to switch between various cell types. So by default, it's a Python code, but if you just click on a cell, so it's not active, but you are more in like a command mode, you can use an M key, and it will automatically switch into a markdown mode, as you can see. And the same with the LaTeX that I mentioned. If you want to use LaTeX, you have to enter the LaTeX, the markdown mode, and then you can just use it to write your formula. And to use LaTeX, you just have to surround your expression with $2 signs. And let's try this. And it will create a nice LaTeX equation for you. There are all kinds of magic commands. I'm not going to go too much into the details. You can also Google it. Just Google for Jupyter magic commands, and it will list a ton of options that you can use. So some of them are particularly useful if you like to experiment and see which part of code runs the best. Is the time and time it. So if you prepend the time with a single percentage sign, this would be an inline command. And if you do the double percentage sign, it will apply to the block of code. And these two are particularly useful as the time will measure the wall time clock for this particular line of block of code that you just ran. So you can see the performance of your code. And also time it is very useful as well, as it does more or less the same as the previous one, but it runs multiple loops of the line of code or the block of code, and takes the average of the best few runs. So if you really want to have the best and the most accurate measurement of the time that your code took to execute, this is the way to go, as it will account for the warm-up time for all the libraries to be initialized, and will be the most meaningful when compared to like a real-world scenarios. Oops. So finally, we get to Python. So Python is amazingly flexible scripting language, and it can be used for so many things. You will find it being used in the clouds, in your computers, in the embedded devices, and it can be used as a website's backend or an API as well. It's really a tool that can be applied to solve a vast number of tasks, mostly because of the amazing community which supplies a package for nearly anything that you can think of. And I think that this comic really depicts what Python is really about. Like, you can do literally everything with it. Now, just as I said before, we'll do a general overview of Python, some programming experiences expected. But before we go into the Python codes, let's quickly go through some features that make Python great, especially for data science. So Python is object-oriented. It does support object-oriented programming. Object-oriented programming is a programming paradigm that provides a means of structuring programs so that properties and behaviors are bundled into individual objects. It helps to get a proper level of abstraction and to not get bogged down with details, but still it allows you to go deep into the details if you really want to. However, there are two twists. So in Python, we do not have explicit encapsulation. What it means is basically that you don't have a private, public, or protected keywords. Instead, Python more relies on a convention that a class variable that should not directly be accessed should be prefixed with an underscore. And it's more of an agreement, and it can be violated. So if there's a method within TensorFlow package, let's say, that you don't like and you want to change its behavior, in Python, you can just overwrite it, change the state of a private field, and then pray that everything still works. There are no guarantees that if you change anything that it's marked as a private, that will not break anything, but you can do it. And also, I think that we'll do in the exercise later in the course. Python has no class interface, but it supports multi-inheritance, so you can the single Python object can inherit from multiple other objects, and we rely on it later in the course as well. It supports multi-paradigms, so you don't have to be limited to using object-oriented programming. You can also use structured programming or functional programming. And also, Python is an interpreted language, so meaning that you don't have to link and compile your scripts in order to run them. Python script is evaluated, just as the name says, as a script. So it means line by line. It also means that some kind of errors will be communicated until the fault line is actually executed. So just that the fact that you can run the main routine of your code doesn't mean that the whole script actually works. You have to actually write a lot of tests to have to be sure of it. Python is a strongly typed language, so it forbids operations that are not well defined rather than silently attempting to make sense out of them. So for example, adding a number to string, you cannot do it in Python, but you can do it in some other languages like JavaScript or PHP. It's dynamically typed, so Python doesn't know about the type of the variable until the code is run. There's also this thing called duck typing. So basically what it means is that if it walks like a duck and quacks like a duck, then it must be a duck. To determine if an object can be used for a particular purpose, with normal typing, suitability is determined by an object's type. So there must be this information provided. But in Python, or rather in duck typing, an object's suitability is determined by the presence of a certain methods and properties rather than just the type of the object itself. Python has a built, just like most of the modern languages, it has a built-in memory management through the garbage collector, and the garbage collector will manage memory and clean any unused data, and it does it by reference counting and cycle detecting. But still, if you're not pleased with how it works, you can still import the garbage collector package and try to manually manage the memory for yourself. So it's more advanced topic, but if you're really into it, you can still use it. The Python itself is designed for code clarity, so the code is very expressive and it resembles English language very much. So for instance, when we write the loop in Python, we do for element in collection. And this will be the structure of the loop. So it's very expressive in this way, and it's very easy to read and follow. One of the things that I like in Python the most is the object introspection. And so by using introspection, we can dynamically examine Python objects. So the code introspection is used for examining the classes, methods, objects, modules, keywords, and you can get information about them so that you can utilize it later in the code. And with Python, if you have access, let's say, to the command line utility, you don't have to like go to the website and browse through the documentation. You can use this mechanism to read all the information about the code itself. Python also supports the interactive mode. So this is the one that you are using when you run the notebook. So this is the interactive mode. So you can run the snippets of the code one at a time, and the interactive mode will remember the state of each of the cells, which also have a funny consequence because let's say that we have a variable x equals 4. Let's run it. Oh, here it goes. So in the next cell, if you want to access this variable, we can just type x and it should output 4. Oh, and by the way, in both Google Colab and Jupyter Notebook, if the last line in the cell is just a statement or command that returns something, even if you don't have a print, this line will be automatically printed out. So this is also very helpful. You can also twist this behavior and make the notebook to print all the lines that return anything. By the default one, it's only the last line. And the funny behavior is that now that we can even like drop this cell, clean it out, and still, if you want to print out 4, you can see that we have no x equals 4 in the notebook, but the state of this cell is still there, and you can still read x as a 4. So it can be also kind of problematic, especially when you have a long notebook and then you want to share it with someone, then someone starts running this notebook from scratch. It doesn't have the state of all the cells as you did. Something was out of order because you changed the order of the cells, and suddenly you have a lot of problems. Okay, back to the presentation. Yeah, just as we said, Python has its own package manager. You can use pip or easy install. Easy install is an alternative to pip, but more or less it does the same thing. And if you have Anaconda installed, there's really no reason why you shouldn't use Conda. Some of the packages will not be available to install directly through the Conda install command line, but if it doesn't, and if you see the error that it's not available, just use pip. If it's not available through the Conda install, it just means that it hasn't been furtherly optimized by the Conda community or Conda company. And also worth remembering, just in the comic book, before you write something in Python, check if the library doesn't exist already, because there's a high chance that you are duplicating someone else's work. So, okay, now that we are done with formalities, let's get our hands dirty and remind ourselves of the most common and widely used data type, the data types available in Python. As a data scientist, we will be relying more on arrays than lists, and we'll be covering arrays in a few slides, but still it's important to know a thing or two about Python's lists, as we'll be using them a lot. Actually, I can't recall when was the last time I wrote a Python script and did not use a list. And also some of the knowledge from the lists can be applied to the arrays as well. So yeah. So if you want to initialize a list in Python, you just have to use the square brackets. So if you run it, you will not see any output, as just as I said, this particular statement doesn't return anything. But if you want to see the content of the mylist variable, do this, and you will see that. Let me zoom in. You will see that this list is empty. If you want to pre-populate the list with elements, you can use the range command. So this will generate, this will give you, at this moment it's not yet a list, but it will give you something that can be turned into a list of 10 elements. So as you can see, this is this weird construct. In Python 2, this would have been a list, but in Python 3, it returns a generator. So if you want to make a list out of it, you just have to cast it to the list. So we can make this construct, and you can see that you just got a list of 10 elements. To access any of the elements, just as in other languages, you can access it via index in the square brackets. In Python, there's also this particular construct. Let me print this list here so we can see it. We can access the elements from the back. So if we want to access the last element, we can access the -1 index. And basically, this will grab the object from the back. And using the same construct, we can grab the 4th element from the back and so on. And this will work just great. When we talk about indexing, we also have to talk about slicing. So slicing is basically a way to access a sublist of a list. So let's say that we want to access elements starting from index 4 all the way to index, so let's say 8. And as you can see, it just yielded us the part of this part of the original list. It's worth noting that using this construct, the left part of the range is inclusive and the right part is exclusive. So it will go all the way to this point, but it will stop actually working somewhere here, exactly here. And so if you want to grab using slicing first 8 elements, you can just do this. 0 doesn't have to be explicit. You can have just a column with 8 and it will work in the same way. And this will be more or less the same with arrays. So we can create a to-do list with Python, but also it's worth mentioning that people often call to-do list, two-dimensional list a to-do array, but it's actually not the same. A to-do list is more precisely a list of lists which only sometimes happen to be of the rectangular shape. What is the difference between to-do list and Python's array, you may ask? So for 99% cases, you are fine with lists. If you haven't used Python arrays so far, then most likely you just never needed it, and that's fine. So arrays by definition are homogeneous. So all objects within array must be of the same type. And on the other hand, the Python lists are heterogeneous. So they don't really care about data type. So in Python, you can create a list that is a mix of strings with numbers, and it will be just fine. There are, although, certain consequences of using either of them. So arrays tend to be faster and more memory efficient, but for some operations, they can be super slow, like expanding the array with a new column or a row. It's because the array is an object that is pre-allocated. All the cells are already allocated the moment you first use the array. So if you want to use another column or the row, it means that Python will have to go and create a whole new object that is of a larger size than the previous one that you've been using, copy the contents of the old array into a new one, and then populate the new row or column, whatever you've just created. And the array module, on the other hand, is also very useful to interface with C code. So if you have any C code that uses C arrays and you want to use them in Python code, you can use Python array and the two are compatible. So that's kind of great. Lists are heavier. Python lists are heavier, as every single element is a Python object. But on the other hand, adding new elements is so-called amortized. It happens in amortized constant cost. So in most cases, whenever you append something to the list, it's in a constant time and you don't have to be worried about the performance. We'll not be going into more details on Python's arrays, as we will be covering something much more interesting in 2 slides that also happens to be array, but not just a pure Python array. So also, let's go back to the two-dimensional list. So if you want to create a two-dimensional list, let's say that you want to create a list with 2 rows and 2 columns, and the list that we'll be creating will not be jagged, meaning that all the lists in the second dimension will be of the same length. And we can use multiple ways to do it. I will present two here in this presentation. So the first one is uses the thing called list comprehension. And so list comprehension is this nice construct that allows you to run different operations on a list within a single line of code. So it's an inline. And in general case, it has a syntax like this. So we have a variable x for x in a collection. So basically what this thing will do, we create a new list that will contain all x elements from the collection. And in our case, if you want to create a two-dimensional array, let's say that we want all the values by default to be 0, we can create this thing times column. So this thing by itself will create a single dimensional list of length c with 0 elements. And we want to do it r times. So we have to change this thing here. So this will create a generator that will allow us to iterate over it exactly r times. So 4 in this case, and then we really don't care about the value of the range, as we'll not be using it. So we can just use an anonymous variable here. So to keep the list working, and voila, here we have it. So we have 4 rows. Each one has 5 elements. And just as with, because it's a list of lists, so if you want to access any of the elements, you can use still the Python standard indexing. So this will return the first row. And if you want to access second element in the first row, we can use this thing as well. You can also use slicing with 2-dimensional arrays. This will return first 3 rows. But unfortunately, if you want to, let's say, take first 2 rows and then first 2 elements in columns, then unfortunately, this will not work as you expect. It will only return the first 2 rows, but will completely ignore this thing. At least in Python lists. In the arrays, the special kind of arrays that we'll talk in the future on the next slide, it works a little bit differently. Okay. So yeah, I hope that everyone has been able to follow so far. And if you didn't, or you want to do it later at your own time, later today I will take all my slides with all the code that I just written, and I will share it on the Slack. I will upload this presentation to Google Drive that Professor Miński mentioned, and then I will share the link on Slack. What time do we have? Okay.
Still about 1 hour.
Ah, that's great. Sorry for a moment of silence. I had to take a sip of coffee. So another Python data structure that you will be using a lot is a dictionary. So dictionaries are a key value store. And the really interesting aspect of dictionaries in Python is the aspect what can be a key in a dictionary in Python. So if you want to create a dictionary, you just have to use these curly brackets, and so any of the elements. Well, let's create some dummy dictionary here and print it out. As you can see, nothing too fancy. As we've been using strings here as a key, but yeah, what can be a key in a dictionary in Python? So dictionary key must be of a type that is immutable in Python. So for example, you can use an integer. Float can be a key of a dictionary as well. You can use a string, just as I did right here. And you can use a Boolean value as a dictionary key, although it's not a particularly useful thing, as you'll only end up having 2 keys if you stick to Booleans. But of course, you can mix the types of the keys, so you can use strings and ints, and it will be okay. However, neither a list nor another dictionary can serve as a dictionary key because lists and dictionaries are mutable in Python. But there is this thing in Python called tuple. So tuple is a very similar thing to a list, but with one caveat: it's not mutable. So it's mutable. So you can use it as a list, but once it's created, you cannot modify it. So there's this, and this is this. So actually, let's create. Oops. Let's go back and let's create one of the keys to be a list, and you'll see what I'm talking about. So this is a list 0, 0, and we can try to assign whatever to it. And yeah, unhashable type list. So we cannot use it as a key in our dictionary. But if we convert to tuple, tuple are just like a list, but with standard brackets. Suddenly it works. So if you are using any kind of dictionary to store any geographical data or nested classes for classification in deep learning, you can really use tuples. to have this nice nested structure of keys that have values assigned to it. And just as with lists, you can use dictionaries. The dictionaries can be created with a comprehension. So this is a dictionary comprehension. So the syntax is very similar, but instead of having just a single value here, we have a key. We have a value here for key in range. Let's say we want to create 5 elements. And yeah, actually, we don't have value. So let's say that we want to do this thing. So this operator, asterisk, it's a shortcut for power. So it will take a key and raise it to power of 2. This symbol is called asterisks, but you will hear me calling it star because it's so much easier to pronounce for me. So whenever I say star, I really mean the asterisks. Okay, so in one single line, we created a dictionary that has iterative integers with a power of 2 as a value to it. And with both lists and dictionary comprehensions, you can extend it with some additional logic. So let's say that we are interested only in even keys, if the keys are integers. So we can do this thing, and this will automatically create a dictionary that only has even keys. So if you want to access any of the values stored in the dictionary, we can use the standard way. Oh yeah, I just deleted the, oops, my mouse died for a moment, sorry. We just deleted this dictionary, so A doesn't exist anymore. So let me comment this out. So we have one here, but if you want to, let's say, access the dictionary in the loop, and access the loop at the end of your inference process in deep learning or other machine learning processes, you can iterate over pairs of values. So for key value in our dictionary, dot items, and so we can print these 2 values. And yeah, it will just go over all the pairs of the key values and print it out here. And so basically, that's how you can use dictionaries in Python. Oops. So later in one of the exercises in our course, we'll be using a global variable. And to better understand how it works in Python, we have to take a look into scopes. So variable scope says where in the code we can refer to the particular variable. And we can do a short example here. So let's say that we have this variable x equals 4, and we have a function. Let's define ourselves a function that will just grab the x and return a number one higher than it. So if we run our function, no surprise, this function has access to 4, so it works just fine. But then if we want to not only make a read to this function, so read is usually global by default, so we don't have to make any additional steps. But let's say that we want to change this variable here instead of here. So this should yield an error. So here you can see that even though the x was defined before, Python will complain that the local variable x was referenced before assignment. And there's really a simple way to avoid it if you want to. You really should not use global variables unless you really have to by design. We'll be using it in this way by design later in this session, but unless you really want to and you're aware what you're doing, you really shouldn't, because it makes your code less readable. Because if you have like thousands of lines in your script and there's a global variable all the way in the top, you will never know what's the current value of it, and it will make your code super hard to debug and follow. And in case of Jupyter Notebook, yeah, because the state of the cells is maintained between different runs. If we comment out x equals 4 and use this variable as a global and keep incrementing it with every execution of this cell, we can see that we'll be going up and up with this number. So it's also something to be aware of. So why I'm talking about it is because in TensorFlow, there's a very similar mechanism based on scopes that allows for managing graphs. But yeah, we'll talk about it a little bit later. Nothing too fancy here. This is a short slide. I only have two operators that I wanted to show you very quickly, which I think are still quite useful in your daily life. And so one of them I already showed you. So this is the power operator. So if you want something to be written to the power, you can use this construct, the double star. And it will work just fine for you. But the other one that I think people are forgetting the most about, and that is also quite useful, is the floor division operator. So usually when you divide, let's divide 3 by 2, you will get a float number. But sometimes, just sometimes, you want this thing to be an integer, and you're interested it to be a value of 1. So most of the time you'll go and just convert it to int, and it works great. It does work, so why not? But there's a simpler way. You can use 2 slashes and run it, and this will do the same. So basically this will run the division and then just flow it down the closest integer. Oops. So anonymous functions. They're also called lambda function, if you have heard this name. They allow for defining a new function in line. It's a very useful tool that you will find yourself using a lot in Python, as it gives you the flexibility without sacrificing readability of your code. So let's see a simple example. Actually, let's write a very repetitive function. So we've been already raising numbers to power. So let's write ourselves a function that will do the same. If I could almost spell return. If without any surprise, if we run this function, it will return 4 without any surprises. So this is the normal function, the standard way to define a function. But in Python, we have this thing called lambda that allows for inline definitions of the function. So we can use the lambda keyword. Then we can define a set of parameters. There can be more than one. You can separate them with commas and have multiple parameters. In this case, we'll be using only a single one. And do the same thing. You don't have to specify return here explicitly, as this expression after the column will be returned by default. So if we run this code, it should yield the same result. I made a typo. So if you were following the screen, there was a typo. But yeah, it works in the same way. And why it's useful and where you'll find using it the most in Python is with a filter and map built-in functions of Python. So let's create ourselves a list of 10 elements. We don't really care what they are, so let's just create a list like this. And then let's do the filter first. And so filter basically, it's one of the most useful built-ins in Python. So it will take in a collection as one of the parameters. And as the other parameter, you can pass to it a function that will be used to filter out your collection. So in this case, let's say that we want to use actually you have to define the function first. So let's go ahead and do the lambda function again. Let's say that we just want to grab all the numbers that are even. So every single number that modulo division returns 0, and then we can pass our collection here. And this will actually return a filter object, which is a generator. This is one of the performance optimizations in Python. So if you don't know what's the difference between a function and generator, is that the function, when you call it, and the function, let's say, that returns a list of 1,000 elements, when you call the function, it will allocate the place in the memory for 1,000 elements at once. If it works, then it's okay. But if you really care about the performance and you don't need access to the whole list at the same time, it's not the best thing to do, as this will hurt the performance. So you can use the generator instead. So you can use generator to do the same thing, but in a bit different way. So with generator, you can yield a list element by element. So in this case, it will return the first element when you need it. And then if you ask for another element, it will yield the second element, and so on until you have used the whole list. In Python, if you want to access the whole object that was yielded by the generator, you can just cast it to list, and it will take all the elements. It will return all the elements at once. And another example is the map. So map is also one of the most useful functions, and you really do use it a lot in deep learning when you do it in Python. So map basically takes the collection and a self-defined function and applies and runs this function on each of the elements of your collection. So again, we can define our lambda here. Let's reuse our power example. You can also, instead of writing lambda x, you can just use power to lambda that we defined before. It really doesn't matter. And as you can see, it took the input list of the elements from 0 to 9, and it applied this operation on all of the elements separately. Asterisk arcs and star KW arcs. So in all frameworks, being it TensorFlow or PyTorch, sooner or later you will meet a function that has star arcs and star KW arcs in the definition. So what are those? What is it? So let's do it by a simple example. So let's create ourselves a list to better see what we are dealing here with. So we have a simple list, 3 elements in it, 1, 2, 3. And so this means that this construct is with asterisks. It doesn't mean that we are multiplying this collection with anything. In this particular case, it's used for unpacking. So if you run this line, it will create 1, 2, 3. But if you just pass a list here, you will see that it is more of a list type, the thing that you just printed. Why is that? And you might notice something very similar if you do something by hand. So you see that this thing actually returns the same thing as unpacking the collection. So basically what it did is created this expression in a single line with this single star before it. You see? So this is more or less how it works. It can be used in functions, and we'll get there in a moment. But one of the useful ways actually for it, other than using it as arguments, the function that you will create, is actually you can use this expression to extract certain members of your collection. So let's say that we have raw data. It will be a list that will have a label. It will have some features like width, height, and let's say depth. It really doesn't matter. So if we print the raw data, we see that like nothing too fancy here. But what we can use this unpacking for is we can specify things like this. Let's say that we want to grab the first column from here, and we can use this construct. Hash data, and yeah, you can take your guess how this will look, but sorry. Yeah, you can see that with this construct, without this star, actually, it will read an error. You cannot do it. You can do this if the raw data would contain only 2 elements, so able and width, but if it has multiple elements, oops, sorry, there must be some unpacking done here. So here we want to define that we want to divide our list into 2 separate beings, one being a label and then the rest of the data. So this will mean that the raw data, after extracting label, will be all packed into this data variable, and it's not very well known, but this is something if you want to do, you can do if you want to. Yeah, but the most common place where you will see the star arcs is in the function definition. So let's create for ourselves a dummy function. Let's what we can do. Yeah, let's roll a dice. So in here, when we have a function with star arcs, it means that we do not specify how many arguments this function expects to have. So it can be a single one, it can be 0, it can be 10 elements, and all of them will be accessible as a list of arguments. Let's see how it works. So yeah, this function will take in a list of dice, plural, I guess, a list of dice, and turn, and we'll return the sum of random casts. If only I could spell it right. Yes, we have to first import this module. So randint, what it will do, it will randomly generate a number in the range from 1 to a given die. But this package is not, we have to import it first, this method. So it's available in the random package. Let's go here. And we want to do it for every die in arcs. Okay, so let's roll. So we'll give it a single dice with 6 rolls. So if you run it, we rolled 5, we rolled 2, but this function doesn't really expect us to, doesn't force us to use a single argument. So we can use multiple ones. In this case, we also rolled 5, but this is just by accident. Oh, I was the most lucky person to roll 5 multiple times in a row. But basically, it will take as many arguments as you want to specify, and it will still work. And it's a rather useful way if you don't want to use, if you don't want to force user to the definitive implementation of your function. You can allow them to pass multiple arguments, although they are unnamed, so they can only be passed as one by one without actual naming them. So if you have named parameters, this thing will not work, not at least in this particular example. For this, we can use the Tartar KWRX. So this thing. So it has a very similar concept to argument list, but instead it's a dictionary. So it allows you for specifying a key as well as a value. So let's do a quick example. So let's say that we want to generate an XML entry from our data. We can pass a label, which will be a defined argument here, and we can give it some attributes. It doesn't really matter how we name these things. I name it here arcs, but I don't know, you can name it dice and it will work fine just as well. And here, it also doesn't matter which name you really use. So in this case, this attribute will be a dictionary. So whenever we pass anything here, it has to be a named parameter. Let's do something about it. So here, the user will be able to pass unspecified number of named parameters. So in the XML, if you want to have them as values for a given tag, We can use this construct. So here we will actually, oops, sorry. Let's do this. Oh my God, this is terrible. How it fills all the signs for you. So let's create a string for us that will be used to create the whole thing. So here we will go for name and value. For name, value in attribute items. So just as we discussed before, so this is a dictionary, so it has a list of items which are pairs of name and value. And here we'll apply the key, which we have as a name, as a keyword to this string that will be part of an XML tag, and we also pass the value in this position. And with this construct, we can, this function can do this thing as well. Let's finish this example and we'll move forward as we're actually running short of time. This example is not that relevant. I just want to show you how it's okay, no errors there. And let's just call this function data to XML. We have my label, and we want to pass some data. Let's say that we have a width of 10 and height of 20, and an attribute list is not defined because I made a typo. And as you can see, using the keyword arguments, we created ourselves a nice XML entry. Not the most useful one, but still, it shows you the concept of how to use the keyword arguments. So here I had prepared a short list of what you can do to make your Python code better, but actually I will just skip this slide as we don't have that much time, and this is just a text, so you can follow it up later when I share the presentation. So it's just, in a short, this is just a guideline on how you can use Python tools to make your code more readable, and how to structure your particular Python projects to look very professional, so that you can upload it to GitHub and then maybe share it on your resume and have a nice thing to talk about. So the NumPy, the elephant in the room when it goes for animation or deep learning. So NumPy, what is NumPy? So now that we have refreshed our Python, it's time to learn about our first Python data analysis library in this lecture. So this is called NumPy. NumPy is a linear algebra library for Python. It's super important for data science. Almost all Python data-oriented libraries rely on NumPy as their main building block. So you have multi-dimensional matrices that you can define with NumPy, and all other implementations in TensorFlow or PyTorch or the tensors themselves, they take a lot of inspiration from NumPy arrays. And basically, just a word, tensors are similar to NumPy arrays. So the multi-dimensional arrays or matrices, as you can call them as well. With the addition being that the tensor can also be used in the GPU. By default, if you use NumPy, if you do any operations on the NumPy array, they will only run on CPU. And if you know NumPy arrays, it's easy to jump into the world of tensors, as the two share a lot of common features and both can interface with each other. So Python being an interpreted language, one might think that processing huge arrays of data will take ages, but again, there are C libraries bindings that Python relies on, and NumPy actually is written in C. It's only the Python interface that you are using when you're running Python scripts. And so NumPy and Python can be really blazingly fast. So how do you get NumPy? again, super easy with either Python's package manager, pip, or with Anaconda. If you want to use the most of your CPU's vector extensions, you really should use the latter one. Once it's installed, you can do it with within the notebook. If you have it installed, you can install it with a CLI, or you can also use the exclamation mark pip install NumPy straight from your notebook without having to go to the CLI. But also a word of caution: if you are using Conda and you want to install a Conda package from the Jupyter Notebook directly, you have to use the -y. Without it, by default, Conda will ask you if you really want to install this version of NumPy with all the dependencies. And because when you run a command from here, it's not in the interactive mode, this command will actually never finish to execute. It will just like hang on waiting for you to type yes, but you really can't. So if you use Conda, remember to, if you use Jupyter Notebook to install the packages with Conda, remember to add this thing. So once it's installed, you can start using it simply by typing NumPy, import NumPy as np. You can just use import NumPy, but then the whole world really inside the code names NumPy as np. So this is a nice short alias, as you will be typing this thing a lot. We talked briefly about RIs. So let's go back there quickly and reiterate over what's the difference between the two. At the implementation level, the RI essentially contains a single pointer to one contiguous block of data. This does have consequences in both usage and performance. Because of the single pointer pointing at the head of the RI, we have to make assumption that all objects in the RI are of the same size. So at the low level, we can easily calculate the memory address of the cell. So for instance, the integer takes 4 bytes. So to access the third element in the integer RI, we have to move the pointer by 8 bytes from the pointer that points at the head of the RI and read the following 4 bytes. With various data types, it would have been impossible. So that's why RI can only use a single type. And another consequence is that RI gives us quick access to both read and write to any given cell, but it's also super time consuming to extend existing RI with additional rows and columns, just as we discussed before. The Python list, on the other hand, contains a pointer to a block of pointers, each of which in turn points to a full Python object like the Python integer, just as we also saw earlier. So NumPy RI gives you a huge performance advantage over Python's RIs, and that's why we'll focus on using NumPy RIs instead of Python RIs. But still, it offers you an edge over even Python lists, but in some operations, and not only because it's an RI, but also due to the approach that NumPy takes to all operations on RIs. So instead of treating the RI as a collection of elements and executing a given operation on each of the elements, NumPy takes advantage of the vectorization and applies the operation to multiple elements of the RI at once. In modern CPUs, you have dedicated hardware registries actually called vector registries. The examples are the SSE and AVX registries. That are capable of operating on multiple operands of the same type or size at the same time, introducing a parallelism that is generally referred to as a single instruction, multiple data, or SIMD mechanism in short. Without vector registries, the data would have been processed just like a standard Python list of RI. So it means one element at a time, or a single instruction, single data, if you will. So NumPy RIs, how to create them. As a data scientist, this is one of the things that you'll find yourself doing over and over again. So it's good to memorize some of the available options here, as there are many different ways to create and initialize a NumPy array. I'm sorry, I have to take a short break. To create a single dimensional list or array in Python, we can actually start with using a Python list. So we can have a list with few elements. Actually, let's set 0. I don't like to start with 1. It's not MATLAB after all. And we can use numpy.array and pass the mylist variable here to create a numpy array. Oh, name NP is not defined. Oh, maybe I didn't run the import before. So if you didn't do it just as me before, this import should fix this problem. And if it complains that you don't have numpy installed, you just have to run or the same with Honda at the top of your cell, and it will fix this issue as well. In the same way, you can convert two-dimensional lists from Python to a two-dimensional NumPy array. So let's quickly define ourselves the 2 dimensions here. Let's have more elements. Why not? We have our matrix here, which is still a NumPy list of lists. But we can just use the same construct, and we've used a few lines above and have a NumPy array. It's also nice that if you print out NumPy array, by default it's formatted in a nice way, so it's more readable, everything is padded. So it's really nice. However, we will be using NumPy most often other built-in methods to create NumPy arrays a lot faster. But if you have a pre-existing Python list, you can just stick with using this thing. So similar to Python's range, we can create a NumPy array using a range and just pass a range of integers that you want to create. You can see it's very similar to Python construct. Also, if you want to start from 0, 0 is optional. You don't have to define it. It can be done this way. You can also, if you can also create a range of NumPy of numbers in NumPy array using every other number with a specifying third parameter, but in this case, the 0 has to be explicit as the third. We must have access to the third parameter, which without 0 would actually we wouldn't have it. So the range wouldn't be valid. Once we have our NumPy array created, as you can see, it's single dimensional, but we don't have to limit ourselves to single dimensions. We can reshape it something else. So here we want to take this one-dimensional NumPy array of 10 elements and reshape it into a 2-dimensional array with 2 rows and 5 columns. You just have to remember that the size of each of the dimensions, if you multiply them, it must be equal to the number of numbers that you've created in the first place using the range. So if you would use something like this, it will just complain that we cannot reshape array of size 10 into this shape because this expects 12 elements instead of 10. Let's go back here. So this will create an array, but as you can see, it's like a sequence of numbers, which might be useful, but I'm having hard times with coming up use case for it other than these presentations. So you can also always initialize an array of zeros with if only I didn't do a typo there. So this will create a one-dimensional array with 3 elements. We can always go and create multiple dimensions, but then instead of specifying a number here and going for this, this still must be done within the first parameter. So we have to create a tuple that will contain the size of all the elements of the NumPy array that we want to create. So We can create a 3x3 array, or we can go for more than that and create a 3 dimensions of size 3x3 on each of them. But it gets more complex to display if you go for more dimensions, so let's stick with this one. And similarly, instead of using zeros, if you want to initialize your array with ones, yeah, you guessed it, you can just type np ones, and this will create the same thing, but with ones. Another useful way to create an NumPy array, and it's particularly useful when you want to draw a plot of something, is to create a linear space, the array that contains a linear space. So you do it by typing lin space. Here you have to specify the range. So let's take elements from 0 to 10, and we want to generate 100 elements, and let's say 101 to be inclusive on both sides. So this will work similarly to range, but with one exception, that instead of generating integers in this range, it will generate a sequence of evenly spaced floats within this range. So as you can see, we have 101 numbers in the range from 0 to 10. And it's very useful when you want to plot something and you need something to fill the x-axis with. I also had a few other examples that include how to initialize random arrays, but I will let you follow up with it later when I share the presentation, as the time is running short and we have more interesting topics to cover. So yeah, the Python dimensions. Let's use an example here. So we all are in the same space. So let's create another NumPy array with 1 to 3 elements. So in this example, let's say these 3 numbers represent the coordinates of a point in a 3D space. So this array has a single axis, and this axis has 3 elements in it. So we say that it has a length of 3. We can extend this example by creating a 2-dimensional array, just as we did in the previous example. What did I do wrong? Oh, okay. It has to be a list of lists. So in this example, the array has 2 axes. The first axis has a length of 2, and the second axis has a length of 3. And while it seems like it's quite easy to follow through, if you have multiple dimensions, it really gets confusing. So it's really nice to remember all of those things. And you also have a set of helper methods with NumPy that help you to follow up if you feel lost. So let's assign it to the A variable, and so we can use the ndim, and it will tell you the number of axes or dimensions that your particular array has. You can also use dot shape. So this will return a tuple of integers indicating the size of the array in each of the dimensions. For a matrix with n rows and m columns, shape will be a tuple n and m. And the length of the shape tuple is therefore the number of axes returned by ndim. And another one, if you're interested about the size of your array, you can use this, and this basically is a product of your shape. So in this case, it's times by 3. We have 3 elements, and these set of functions are really useful if you have multiple dimensions and you feel lost in your data, and you get errors that you're accessing an element in the dimension that doesn't even exist. So the data types, as we said, the NumPy arrays are homogeneous, so it means that you can use only a single data type. You cannot use strings, a mix of strings and integers. You cannot mix int with floats, it's prohibited. But when you define the array, NumPy will automatically try to figure out what's the given type for your array. So if you check the d type, you will actually see that this is a 64-bit integers. But if you would pass floats to it, it should change and the whole array will be of type float as well. But you don't have to rely on NumPy to get the data type for you. You can define it during the initialization with constructs like this. So even though we passed a set of floats to the NPRI, we forced NumPy to use it as an integer instead of a float. Indexing in NumPy. So do we have access to another list? Yeah, we do. So great. So we can see that the state of the previous cell carries over. And actually, I'm not sure if you noticed, but this presentation uses Jupyter Notebook with an additional plugin, which allows me to have a mix of Markdown with Python code that I can run in my window. So if you want to access data stored in a NumPy array, we can use the same syntax as we've used. Oh, someone has closed the presentation plugin again. So the presentation plugin that I'm using is called Rise. So you can install it once you have Jupyter Notebook installed. You can just use pip or conda and install Rise, and then there will be additional button in your presentation that you can just click and it will pop up in this way. But that's just on the side note. So you can access your arrays in the same way as in the Python list. So you can use this construct if you have more than 2 axes or dimensions. But the more popular way to access indices in NumPy is using single square brackets with a comma inside. It will yield the same result, but you will see people more often using this approach than the other one. And basically, the comma-separated indices became a gold standard for getting a value out of an NumPy array. And just as with Python lists, you can use colon to access the whole dimension. So here, basically, let's print the A as well, so we see what we are talking about. So yeah, here we can see that we grab all rows, but we are only interested in the column with the index 1. So we actually grab only the 25. But we can do it in the multiple dimensions. If you have more elements, you can do ranges like this, and this will create nice slices, square slices of the arrays that you can cut out. So it doesn't have the problem that I mentioned in Python lists. You can easily access elements like this. So Boolean masking. Sorry for rushing right now, but I'm really running out of the times, as Professor Miski reminds me. So Boolean masking is one of my favorite party tricks that I like to use to impress people at the bar. So when we index arrays with integers, we are explicitly providing the indices to pick. With Boolean indices, however, the approach is slightly different. We explicitly choose which items in the array we want and which ones we don't. The most natural way one can think of Boolean indexing is to use Boolean arrays that have the same shape as the original array. So let's very quickly range. Let's create ourselves an array of numbers. Let's reshape it to something that has more sense for this example. So as you can see, we have a 2-dimensional array that has its shape. But now that we have this array, we can write a condition to it. And as you can see, this expression actually returns the array that is of the same shape, but it is a false and true values, a Boolean values. So at every index of this array, let me quickly print this thing here as well, so we see what we're talking about. It says whether this particular condition was met or not. And while it doesn't seem that useful right now, but the fun thing in NumPy is that we can actually use this expression, this much larger than 4, as way to point ourselves to index. So as you can see, even though we have 12 elements, by passing this Boolean mask as a filter for indices, we get ourselves an array that contains only the elements from the original array, but only those which met the criteria that we've defined in this filter. How much time do I have? Not much, unfortunately.
Actually, no time. Actually, no time. Let's conclude 1-2 minutes and leave some 1 or 2 minutes for questions.
Okay, so I will just briefly go over what I wanted to talk, and I really wanted to talk about everything. And in my practice sessions, I actually managed to fit everything into hour and 40 minutes. But somehow I was too talkative today, it seems, and I talked too much over the first topic. So, but yeah, don't worry. I will post this presentation with all my notes later today, so you can follow up if you want to. So the topics that are particularly interesting are next is the NumPy broadcasting, NumPy operations. And here you can see that it's an empty code, but I will take my time and I will fill all the examples that I wanted to do. So you'll be able to run this code in your Jupyter notebook, and you will be able to see all the examples that I've prepared. We have various operations on NumPy. I wanted to go for the data visualization using the matplotlib to plot all kinds of data that you can store from NumPy. I prepared a real-world example using Iris dataset, which I really wanted to get to. It was really nice that it even includes the 3D graphs that you can move around in Jupyter Notebook in the interactive way. You can play with it. I had a dimensionality reduction because when you have data in your machine or deep learning problems, usually you have more features than you can actually display. Even if with the simple data set as Iris, you have 4 or 5 features. So if you want to plot your data or visualize it in a graph, it's not as very straightforward way because we can only see up to 3 dimensions or 4 if you create a movie out of it. But basically, there are a really simple way to reduce the dimensionality of your data to be able to visualize it and still do not use a lot of information. And someone asks about the TSNE. Yes, so actually I was going to use a PCA in here, but TSNE is also another great example of dimensionality reduction algorithm that can be used. So I haven't used TSNE in a while, so I don't remember exactly what's the implementation details in it, but in PCA, basically the PCA algorithm looks for the feature that has the least impact on the overall importance of your data. It removes this feature and adjusts the rest of the features so they can accommodate a little bit for the loss. So the easiest example is for the dimensionality reduction algorithm is to imagine a tree. It's a real 3D world object that has a width, it has a height, and it has a depth. And the tree casts a shadow, and this shadow, it doesn't have all the features of a tree. It only has width and height, which are not the same. They have been adjusted to accommodate for the loss of depth. So this is how the dimensionality reduction works. It works in a loop, and you can even reduce 100 dimensions into 2. Obviously, we'll lose a lot of data, but it will allow you for it. Yeah, I was going to go through Pandas. Pandas is a nice library. If you have data stored in a comma separated value file, it allows you for a lot of data exploration, get to know your features to see if any of features that you are actually about to use is really that important, and what are the statistical characteristics of your data. It's also really important. So I will include everything here, so you'll be able to follow through if you want to. And then just before jumping into TensorFlow, yeah, I know, 1 minute more. Sorry. I had an example of graph computing. So this is a concept that both TensorFlow and PyTorch relies on. And actually, we were going to write our own simple graph processing framework. We were about to define like all kind of operations that a simple graph might use. placeholders, so the things that you can expect in TensorFlow and PyTorch, how to run this session, and then at the end, the same example with using TensorFlow 1.x session example, and as well as a TensorFlow 2.0 or newer with an eager example. But yeah, everything will be available later today. So yeah, sorry I didn't make it through. I talked way too long for an easier topic and didn't get to the more meaty stuff.